Welcome everybody to another session from Neuro Research. I'm Srijit here, and today in this session, I'm going to brief another application using AMS band, which is known as NEGF. NEGF is a non-equilibrium green function, which can be used as a powerful method for theoretical calculations, or else to study the quantum transport in nanoscale systems and devices. It allows for the calculation of electronic properties such as transmission functions and current under non-equilibrium conditions, where an external bias voltage is applied. So this is actually a basic introduction about NEGF and how we can incorporate it with that. So as an introduction, AMS, which is a comprehensive software package for computational chemistry and material science. Within AMS, the band module is a density functional code, or DFT code, specifically designed for periodic systems, which includes crystals, surfaces, and nanowires. So speaking about NEGF within AMS band, the band module is in AMS incorporates the NEGF formalism to enable the simulation of electronic transport through nanoscale junctions and devices. So you can see in this specific session, I'm just taking care about NEGF. So how we can start the NEGF session. So under task, I'm just selecting this NEGF and then later going into the brief scientific explanation. So how we can implement using band. So the band implements a self-consistent NEGF approach. This means that the electronic structure of the device and the transport properties are calculated until a consistent solution is reached. So speaking about the transmission function, it's a primary output of NEGF calculations in band, and the transmission function describes the probability of an electron with the energy being transmitted from one electrode through the central scattering region to the other electrode. Current calculations. Once the transmission function is obtained, the electric current flowing through the device under an applied bias voltage can be calculated also. So various applications can be covered within this area. So, and also self energies, the influence of this electrode on the central scattering region is accounted through a self energy matrix, and this describes how the electronic states in the lead coupled to state in the central region and induce broadening of the energy level. So speaking about Hamiltonian and overlap matrices, the central region of the device is described by a Hamiltonian matrix and an overlap matrix. These metrics are typically derived from DFT calculation performed by band, and obviously the green function. So the central quantity in the NEGF formulation is retarded Green's function of the scattering region, which is a calculation-based mathematical method. So how we can set up the NEGF calculation in band. So the NEGF calculation in band typically involves the following steps. First is the lead calculation, which implies how we can perform a DFT calculation for the isolated left and right electrodes to determine their electronic band structure and subsequently their surface green functions from within which the self energies are derived. So in this typical example, I have taken a carbon nanotube and the central region. So you can see the left and right sides of the electrodes, and the central region, this is actually the central region. Setting up the geometry for the central scattering region, which may include parts of the leads to ensure proper scattering, and the transport calculations, combining the Hamiltonian and overlap matrices of the central region with the self energies of the leads to calculate the green function and the transmission function. So this step can be repeated for different bias voltage to obtain the current voltage characteristics. And speaking about the applications, the NEGF implementation in AMS band can be used to study a wide range of nanoscale systems, including molecular junctions, nanowires, graphene-based devices, magnetic tunnel junctions, thermoelectric materials, and overall a general information about NEGF. So this method is a powerful tool for analyzing quantum transport because it can handle open systems, non-equilibrium conditions, coherent and incoherent transport, many body interactions, and also as a summary, In NEGF method, as implemented in AMS band, it provides a robust approach for simulating electronic transport in nanoscale systems from first principles, allowing the researchers or users to gain valuable insights into the behavior and performances of these various devices. So right now I'm winding up. In the next videos, we will be focusing on more calculations and applications of NEGF through band. So thank you for now.